Hello. So this is Math321, and I'm going to talk about Lagrange polynomials. Lagrange polynomials. So the idea here is we know that the polynomials that interpolate a collection of points, where this is considered to be inside some point inside the domain of whatever function I'm thinking about, and this is considered to be the value of that function at the point, and we have n of these things. So we know that the polynomial that goes through these points, whose graph goes through these points, is unique. We proved that last time, and the unique polynomial that goes through them is called the Lagrange interpolating polynomial. And Lagrange interpolating polynomials are sums of polynomials that are themselves called the Lagrange polynomials. So we know that to interpolate this we need to have a polynomial of degree n. So whatever polynomial we have to go through these points will look a little bit like this. It has to. So for each xi, we have an equation of this form. We can consider this to be a linear equation in the ai's. So we need to find the ai's in order to work out what our polynomial is, and we have some xi's, which we know when we plug into the polynomial give us fi. And we have n plus 1 equations. It's a good thing then that we have n plus 1 unknowns. Unknowns being the ai's. So you could solve this system of equations to work out the ai's. We could write it in a matrix form if you'd like to make it very easy or easier to solve. So finding the ai's then is a matter of solving this system of equations, which you should know from linear algebra. There's some issues with this matrix which might crop up. This is called the van der Mod matrix. Probably pronouncing that wrong. The conditioning of the matrix will depend on where you've sampled the function. And it is possible to choose sampling points in order to ensure that this matrix is well conditioned, and so it's easy to solve this. It's not a bad way to approach it, but it turns out that we can write down the polynomial directly without doing this. So that this might be useful if you have an automated system that's needed, perhaps. But we can write them down directly. So this polynomial can be considered to be, we know that it has to be, no, let me write down. So in order to write down Pn directly, direct formula for Pnx. So before I actually give a direct formula for Pnx, I'm going to consider some functions. I'm going to denote Lix. These are going to be polynomials, and in particular they're going to be the product j not equal to I, x minus xj, divided by the product j not equal to I, xi minus xj. So these polynomials are designed in such a way that Lixi, let's say xj, is going to be equal to delta ij. So it's either equal to 1 or 0. It's equal to 1 at xi, and it's equal to 0 everywhere else. No, it's it's equal to 0 at all the other points where we've sampled the function. That's what I should say. So this gives us an easy way to write down the formula for our function. So in this case we can write Pnx is equal to the sum of Fi Lix. And you should check that this works. The point being that at xi, this term will be 1, all the other terms will be 0, and the value of the polynomial will be fi. At xj, similarly, this term will be 0, unless I is equal to j, in which case we get fj. Oh, I. And by the uniqueness of Pn, or by the uniqueness property that we have for polynomials, this must be the interpolating Lagrange polynomial. Which is pretty nice. The question is, or the question remains, how do the AIs relate to this thing? This is a polynomial, and in general one term of this, Fi Lxi, is going to be something that looks like this: x minus x0, x minus x1, x minus xi minus 1, x minus xi plus 1, x minus xn. So in general, Li will itself be a polynomial of degree n, who has roots at all the other points where we sampled the function. This is going to be divided by xi minus x0, xi minus x1, xi minus xi minus 1, xi minus xi plus 1, xi minus xn. And this will expand out itself if you take the product of all of these things into a polynomial that has coefficients of every degree. So working out exactly how the ANs are related to this particular formula for the Lagrange polynomials is not particularly easy, but other people have done the work for us, which is great. There's the definition: let f be a function from R into R. So fx0 is going to equal the value of the function at x0. x0 is in R. And fx0, x1 to xn is going to equal, this is an iterative definition of these things, so this is called the nth plus 1. Excuse me. Apologies. Anyway, this is the nth plus 1 finite difference. And here we have n terms and n terms, so the nth plus 1 finite difference is given in terms of a recursion of the finite difference over n terms minus a finite difference over n terms. You note there's a 0 missing here, and there's a there's an n missing here, and there's a 0 missing here. So my claim is that if we write Pnx equal to a sum of products a0 plus a1 times x minus x minus x0 plus a2 x minus x0 times x minus x1 plus and so on up to a n x minus x n minus 1, see 0, 1, 1, 2, times down the product of all terms from x minus x n minus 1 to x minus x 0. Then this is the Lagrange interpolating polynomial when ai is the ith finite difference. Now that's not particular, oh right, and I guess we're defining the empty finite difference to be equal to 1. This is not particularly the same as what we had before, because previously I wanted to know what the coefficient of the x to the I term of the polynomial is, but you can work that out pretty easily from this formula. So if I want to know what the x squared term is, I know it has to come from here. This term will actually generate more terms than that. I'm going to get an x squared term, and that will be the a2x squared. But that a2 will also contribute to the term of degree x and the term of degree x to the power of 0. So I get a2 times x0 times x1, which will be a term of degree 0, and I'll have something like minus x0 plus x1 times a2 will contribute to the linear, the coefficient of the linear term. So while this result is not, I should say claim, so while this result is not quite the same as the one we're talking about before, you can work it out and calculate everything from here. So and of course it's much easier to do the expansion of this than it is to do that. So the proof of this is a bit long, and I'm going to skip over one step a little later on, but it involves finding a new formula for the finite differences, which because of the recursive definition means giving a formula and then proving that formula satisfies the recursive definition, which, because the recursive definition involves fx0 up to the finite difference over f applied to x0 up to xn minus 1, and minus the finite difference of x1 up to xn, we have the recursion is not over the same points. It's a little more awkward than you might expect. So the starting point for a proof of this claim is to note that if we have our interpolating polynomial equal to an interpolating polynomial of degree n minus 1 plus some thing degree at most n. So this is going to look a little bit like an xn plus some other stuff. That other stuff is what I just mentioned before. So if we write that, then we know that for all xj, pn xj, and here j goes up to but does not include n minus 1, this is equal to fxj, which is equal to pn minus 1 xj plus qn xj. But this is going to be equal to that, because this is the Lagrange interpolating polynomial over those points. So this implies that qn xj is equal to 0, and that implies that qn xj, that implies that qn of x has to equal some number times a product j equals 0 to n minus 1 x minus xj. Because we know it vanishes at endpoints. There's my endpoints. It's degree at most n. So So we can find a formula for an, or for an on the basis of this. Fxn is going to be equal to Pn minus 1 xn plus an times this product. And that implies that an is equal to Fxn minus Pn minus 1 xn divided by this product. Now we know what the Lagrange interpolating polynomial looks like. So we know Pn minus 1 of x is equal to sum j equals 0 to n of fxj times the jth interpolating polynomial. When you take this formula, you plug it into that, and you rearrange, this implies that an is going to be equal to the sum of j equals 0 to k of fxj divided by the product I equals 0 up to n, and I is not equal to j, xj minus xm. And my claim is that this implies that an is equal to the nth plus 1 finite difference. Which means I wrote it down wrong on the last piece of paper. So showing that this formula is really the same as that is an exercise in a very large amount of algebra. But you can do it. You can write it down if you wished, and just brute force the solution for it. As an example, we can work out what the various terms might be. So if we now consider n to be running from 0 all the way up to whatever, a0 is going to be the sum over j equals 0 to 0 of fxj over the product I equals 0 to 0, I not equal to j, of xj minus x xi. This is empty, and so this is just fx0, which is equal to fx0. A1 is equal to the sum j equals 0 to 1 fxj over the product. And when you expand the definition, this will be fx0 over x0 minus x1 plus fx1 over x1 minus x0. When you swap that around, you get a minus sign, and that is the finite difference. It's worth noting that this is a formula that's entirely symmetric in the xj's and the xi's. So you can rearrange them completely, which means that the finite difference fx0 xi is actually equal to the finite difference fx1 x0. Exactly the same. So the direct proof is difficult, but it can be done, and you could try it if you want to play with a lot of algebra. Here's an easier way to do it. the Lagrange interpolating polynomial can also be written like this. So instead of counting from x0, I count from xn. And I leave my x0 out. This is identical to the formula before, algebraically at least. The BI's will be quite different. Anyway, when you plug this in, you do the calculation. This implies that each of the BN's is going to be equal to the sum j equals 0 to n f x n minus j over the product k equals 0 to n k not equal to j x n minus j minus x n minus k. Which is very similar to the xn. So I know that this term is exactly the same as the previous expression for Pn with the a's instead of the b's. So subtract the two polynomials and write down the equation for the xn and the xn minus 1 coefficients, or emphasize them at least. And we'll note that Bn equals An. The top power will be the same. And one way to see that is that these polynomials with the Bn's and the An's are exactly the same. We know that it's unique because it's the Lagrange interpolating polynomial. And the Bn and the An are the coefficient of the highest degree term, which would be x to the n. Since the polynomial is unique, they must agree. So they must be equal to each other. Another way to see it is to write down this formula directly and see that all I've done is I've scaled with the j. So if you note that these two things are the same and you subtract the b's from the a's, then what you end up with is 0 equal to x minus x0 minus x minus xn x minus x1 product up to x minus xn minus 1. So this is the term that involves the bn's and the an's. I'm just going to put an an there. And then we get an minus 1 minus bn minus 1 times x to the n plus things of degree n minus 2. And when you solve that, you end up seeing that an is equal to an minus 1 minus bn minus 1 over x0 minus xn. So now I have two formulas for the an's and the bn's, and in particular I have a formula that looks like this. This looks like a recursive formula. We know the bn's directly, so we know, for example, that b0 is the 0th finite difference, fxn, and we can write down b1 quite happily. And using that properly, you can plug the formulas for the bn and the an into this expression here and see that an must actually satisfy the same recursive formula that finite differences do, and therefore must itself be a finite difference. And that gives the result. So we can write Pnx, our Lagrange interpolating polynomial, as the first finite difference plus a second order finite difference plus the nth finite difference and let's suppose that you end up building a Lagrange interpolating for some data, and then you measure some new data and you want to build the new Lagrange interpolating polynomial. Well, this form for the equation just allows you to add extra terms that incorporate the new data points in a very easy and simple way, rather than solving that the van der Moder matrix all over again, which I'm sure I'm pronouncing incorrectly. Apologies. to everyone who knows how to pronounce that correctly, or for starting from the beginning with the expression for the Lagrange interpolating polynomial using Lagrange polynomials themselves. So if aj is equal to the finite difference, no, this is considered to be, this is the same thing as, but I'm leaving the f out because I'm emphasizing the fact that I've measured the points rather than I know the points and how to evaluate the function. But anyway, just swapping backwards and forwards to the notation. And if I let my eta j's equal the product, then I say that Pnx is equal to the sum aj eta jx. And as we showed, Pnx can also be written as the finite difference of fn minus 1 x minus 1 plus and in fact any other kind of combination of starting with whatever points you want to express the polynomial in. And you can show that they're all kind of equivalent because, of course, we know these things are unique. So my suggestion is to I'm not going to write this out, but my suggestion is to do some examples. So pick some points. So this is x0 and this is f0. And then write down the polynomial. This is the polynomial expressed using Lagrange polynomials, and then you can express the polynomial using finite differences. Calculation of finite differences is a little easy if you are happy to tabulate things. Here's my x's, here's my fi's, the finite difference is this minus that divided by that minus that. And the second order finite difference is this minus that divided by this minus that minus that. So this minus this divided by that minus that. It's easy to work it out. You can write down a whole little table. It's, well, I still find it need to calculate it, but it's easier than you might find otherwise. Just as a device for keeping track of the values of things as you do the calculations. You can write them all out by hand if you really want to. Right, and one last result, which proves something I think that I mentioned or claimed very early on in the result. This is a little theorem. So let x0 up to xn be k plus 1 distinct points, and let f be some ck function on the interval I equals the minimum of x0 up to xk times the maximum of x0 up to xk. Then there exists psi x inside the interval, so that fx0, the finite difference, the kth finite difference, so this is a k plus 1 finite difference, kth derivative, so this says that finite differences are derivatives, approximately, and that should be expected because the coefficients of a polynomial are related to the derivatives of the polynomial. evaluated at certain points. So not unexpected. It's a generalization of the mean value theorem. And the best way to say it is that it follows directly from the definition. And an inductive argument, which I suggest you try out. So that's Lagrange polynomials.